In this short video, I'd like to discuss a little bit about the lighting system we are developing. We call it dynamic whites light to aid sleep and vision for persons living with dementia. So lighting is very important for us, and in an aging society, we expect that about 15% of the people will have dementia. Once we have dementia, about 28% of people with dementia will have trouble with falls. And a lot of this is due to difficulties with vision leading to falls. Another 65% of people with dementia will have disturbed sleep patterns. So both these issues are related to lighting. When we are outside, dynamic white light is in God-given sunlight. The intensity is changing continuously throughout the day and night. Unfortunately, as we get older, we spend more and more time indoors where there is insufficient intensity and the light is static and unchanging. This does not provide information for us to understand what time of the day it is. Let's now consider about light in our eyes. They are not just for seeing. So, within our eyes, we have basically three different systems. One are cones. These cones let us see color during the day. That's blue, green, and red. We have rods, which let us see gray at night. And we have another system called PRGC cells. They don't contribute to vision, but rather they control the amount of a hormone called melatonin in your system, in your body. And melatonin is very important for telling when we're sleeping and how our body clock functions. Now, each of these systems is sensitive to a different wavelength. So let's look at this here. So light comes into our eyes. As it enters the eyes, the first thing it senses are these PRGC cells, which sends out direct information to your body about what time of the day it is. The light continues on and then is sensed by either rods or cones, which give us the vision system at the back of the eye. In this graph here, we're plotting the wavelength versus lambda versus both the irradiance of light and the sensitivity. Now, as you can see in this graph, sunlight is a very broad spectrum of light coming through from 400 nanometers to 650 nanometers. For our vision system, for color, our cone system to see color, we have this sensitive area that shows us a blue light. This is a sensitive area for green light, and these tell us red light. Now, as you can see, a traditional light is designed so that there is a peak in output at blue, a peak in outlet at green, and a peak in output at red, so that we don't waste energy. But there's only one problem with this. These PRGC cells are sensitive at this wavelength around 480. And as you can see, sunlight has a lot of radiation in this wavelength, but traditional lighting basically has very little light in this wavelength because it was only about in 2016 and only proven around 2019 that this is important for our sleeping and controlling our clock. So let's compare now how we want to now improve the lighting. Okay, so there are basically, looking at our two systems, the vision and our clock system. For our vision, conventional lighting the light is direct. There will be glare, there will be shadows, and these glare and shadows result in falls. In order to be more healthy, we would like our light to be white like sunlight, and we want to have multiple sources. We would like indirect lighting so that there is no glare, no shadows, and therefore falls will be reduced. In terms of our vision and our clock, conventional lighting inside an old age home has insufficient intensity, only between 200 and 300 lux. So this makes it difficult for people to see clearly and also not sufficient stimulation when you consider sunlight can be up to about 50,000 lux. So for healthier lighting, we would like to, according to the Alzheimer's Society, have sufficient light to see clearly and keep awake. Somewhere between 500 and 1,000 lux should be sufficient. In terms of our clock and our nighttime sleeping, conventional lighting is static. That is, it doesn't change throughout the day or night. There is no indication of time. However, in healthy lighting, should be white like sunlight. While staying white, it should be changing with intensity and the spectrum, although still looking white. And this will provide an indication of time for our body. And secondly, for our clock, conventional lighting, as we just showed you, doesn't have the wavelengths that will allow you to suppress melatonin. The result is people will be sleepy during the daytime. If we want to have healthy lighting, we want to control the intensity at 480 nanometers. In the morning, we want to have high intensity. In the evening, moderate intensity. And at night, no light, no intensity at 480 nanometers. In Resin Gardens, we are trying to implement this. So for vision, to solve the problem of for vision, we are using LED strip lighting concealed in coves in the baseboard. This provides even indirect light throughout the room. In order to provide a dynamic lighting environment to help set our clock, we're using a computer to control intensity and spectrum on the 24-hour day period. And finally, also to ensure that we get light varying at 480 nanometers, we are using 6 different types of LEDs emitting at different wavelengths to help us do this. So here would be basically our system here, and in this graph we can see the time of day and the illuminance in lux that we are having. First of all, the photopic lux, that control is for our vision system. So as you can see at the nighttime, it will be relatively low, but sufficient to allow a person to see to get to the washroom. In the morning, when it's time to get up, it will increase, getting to a maximum at noon, just like sunlight, and then starting to decline throughout the day, getting less and less as it goes to the evening, and then dropping at nighttime back to a low level so one could be able to see where they are going. Note that this will exceed both the minimum daytime P-lux according from the Alzheimer's Society, for the bedroom, and for the common area, as well as, and at nighttime, the minimum lux according to the IES standards. Now, in order for the clock, we are concerned with another type of lux called melanopic lux. That's the emission around 480. How does it vary? Well, at nighttime, you can see it's at 0. So it's basically telling you it's time at nighttime. In the morning, it starts to increase, slightly slower than the P-lux. But by noontime, there is much more melanopic lux than there is photomic lux. So there's a sufficient amount. Then the melanopic lux starts to drop rapidly in the afternoon as it gets time to go to bed, telling your body, hey, it's getting to be evening. We should be going to sleep. And then at nighttime, it goes back to 0. So if the person wakes up at nighttime, they will have no stimulation telling me, hey, it's daytime. My melatonin will not be suppressed. How do we control this system? We have our dynamic light controller, which is controlling these 6 different types of LEDs, 3 types here, plus 2 types on this strip, plus 1 type on this strip. They'll be turned on at the nighttime by a motion sensor in case the person gets up out of bed without turning on the light. Motion sensor for safety will turn on the light if there is motion in the room. There will also be 3-way switches. These will allow the light to be controlled from different places. Using Wi-Fi, these switches can be placed wherever are convenient for the person who is living there. In addition, an emergency switch allows the lights to be turned on to full power by a caregiver in a case of an emergency. And finally, we will be sensing a bed activity sensor will also be providing information to the dynamic light controller saying, is there someone sleeping in the bed? How are they doing? So the heart of this is this small controller system. So this research is being funded by the MOST in Taiwan. If you're interested in more information, you can click on our little our QR code here. And here are some additional references in which you can talk about the prevalence of Alzheimer's disease, the danger of falls, the amount of time, the sleep disorders, along with initial proof showing that dynamic lighting can help improve sleeping.